Howdy y'all, we're for Godspeed, and our project is the Gamma Detection Rover, also known as Gary. So quick overview, we'll go over the team members, team sponsors and advisors, the problem statement, and our project objectives, the basic requirements for us to succeed, the main challenges we've faced so far and will continue to face, concept of operations, and our final design. So our team members, Troy Baxter is project manager, Preston Banks, mechanical lead, Trevor Rose, electrical lead, and Christian Ramos is the software lead. Team sponsors and advisors, Heather Baxter from Northland Portage and Robert White from LBYD Inc. are our sponsors, and our advisor is Dr. Lee. So a quick overview of our problem statement. At the current moment, companies like Northwind have sent out a technician to traverse a 2,000 square meter property to gather radiation levels, 8 to 10 readings per square meter. For this to happen, a technician has to walk over very hazardous terrain, whether that be potholes or just general radiation levels, and hold a probe 8 to 11 inches above the ground, and then a rate meter and GPS unit in a backpack. As you can see in the figure on the right, as time progresses, these readings become more erratic, but they do show that in blue areas that radiation levels are low, while red areas show that radiation levels are high. Due to this inaccuracy and inconsistencies, companies like Northland have to spend several weeks and several hundred thousands of dollars to gather more accurate measurements in order to help with the cleanup process.
So the product objective, the purpose of the Rover is to provide an affordable and reliable autonomous all-terrain gamma detecting vehicle that will save the client both time and money, and whenever they do these environmental radiological remediation projects. It's also going to help preserve the health of on-site workers, and it's also going to help bring more consistent data readings whenever they do these projects.
In terms of basic requirements, the Rover must be capable of both autonomous and remote operation, as well as functioning on a rough terrain, so soil grade C. This includes gravel, sand, and mud. Operate on a 3-to-1 slope, or about 18 degrees. Have a continuous runtime of at least 3 hours. Avoid obstacles on a planned route, and then alert a technician in the event that the Rover becomes stuck, encounters an unavoidable obstacle, or the battery is below 20%. Finally, having a probe be maintained at 8 to 11 inches from the ground.
The main challenges for the project that we're going to be facing is establishing a communication protocol for the rover and technician. The communication protocol can have interference based off weather, based off buildings, and just almost anything that can interfere with the signal. Number 2 is traversing rough terrains and maintaining ideal probe height. Number 3 is height detection due to varying terrain and grass. Number 4 is balancing battery capacity, runtime, and overall weight. And number 5 is supply chain issues and source materials due to the current supply chain issue the country is currently facing.
A rover will collect data at a density of 8 to 10 readings per square meter by implementing a proper movement pattern and speed. A time flight sensor will be used to determine the distance between the base of the chassis and the ground. It will hold a probe at a specified range, 8 to 11 inches from the ground, using a linear actuator and to manipulate the probe height. Full autonomous mode will be incorporated, as well as obstacle avoidance to be able to complete the route. Manual operation mode would be incorporated in case of autonomous mode failure or reaching an insurmountable obstacle. A live video feed to the technician and manual mode input from the technician will be enabled using a Huawei cellular module. As you can see here, it will follow its set path, and going around any obstacles that it encounters, it would continue its set path until either it completes its route or until the battery gets low enough to the point that the technician needs to replace it.
So, the final design for our rover body, with the unique sponsor requirements of 8 to 11 inches for the probe height, a 3-to-1 slope being required, and the resulting necessary weight. Capacity for instrumentation, we were actually unable to find a base model to purchase, and so we have opted for an original design instead. As can be seen from figure D2, the expected rover size is slightly less than 8 cubic meter, with a probe and the associated height control equipment nested in the rear. And this will bring the final weight to about 79 pounds. With the added stability of the square design and paired with the center of gravity tool that we can use in Inventor, our estimated maximum incline for the rover to remain stable is currently 53 degrees, well above our sponsor's requirements. To ensure an adequate density of the readings, the rover will have to travel at 0.4 miles per hour or 0.18 meters per second. The current DC motors chosen based off of the torque requirements are estimated to have a max speed of 0.8 miles per hour or 0.336 meters per second. And then the most difficult component to design and fabricate is our unique suspension. And with each suspension leg, one of which can be seen in figure D1, being required to hold a 20 to 25 pounds. After initial tests, the maximum operational weight per leg is estimated at 84 pounds.
Autopilot mode will be implemented using open source Pilot software on a Pixhawk 4 flight controller and a Raspberry Pi companion computer. The rover will be operated with 4 independent 12-volt DC motors capable of providing 4.5 newton meters of torque each. A 12-volt, 30-amp-hour lithium-iron phosphate battery will be used to power the motors, while the control boards and sensors will be powered using a 6S 20-amp-hour lithium-ion battery. This will allow for a continuous runtime of at least 3 hours. A LiDAR will be implemented for obstacle avoidance, allowing for full autonomous motion.
And the final design for the probe height manipulation, we will custom make a probe holder. This will be designed to prevent damaging of the probe casing, and can be seen in figure D6. A time of flight sensor will be mounted on the bottom of the rover body and will measure the distance to the ground. And then a linear actuator and a set of linkages are going to be used to alter the probe height based upon that time of flight sensor's readings.
The software that's going to be used for this project is going to be the Pilot Mission Planner application. We're choosing this because this application has autopilot and route planning capabilities, meaning that the technician can make a route and then the rover will go and follow that route based on the software. The software can also control the rover hardware to run according to the route specifications, which means that the motors will be controlled based off certain coordinate points from the GPS module within the application. This also has sensor output from the Pixhawk 4, which include the velocimeters, a gyrometer, and also an accelerometer. It also enables live video stream and controller joystick inputs for manual mode. If you look to the right, for figure D7, you'll see the Mission Planner application layout, and for figure D8, that is just a route that was created around the Bonfire Memorial here on campus. And the probe height will be controlled using a custom code written in Python 3.0.
We'd like to give special thanks to our sponsor, President Jeff Scott and Northwood Portage, for sponsoring this project. If you have any questions, comments, or concerns, please leave them below and we will answer them as soon as possible.